Hi guys, just back again trying to continue to solve the remaining questions in the Art of Electronics chapter 2. We have solved all 4 questions on the back of chapter 2. We have a few questions remaining, so let's go ahead and solve question 5, which deals with differential amplifiers. So let's go ahead and get started by reading the question. Question 5 says, design a DC coupled differential amplifier with voltage gain of 50, that is to a single-ended output, for input signals near ground. Supply voltages of plus or minus 15 volts and a quiescent current of 0.1 milliamps in each transistor. Use a current source in the emitter and an emitter follower output stage. So basically I will, in the interest of saving time, I will quickly show you the form of the amplifier that we're supposed to design. So let's take a look here. This is the form of the amplifier that we're supposed to design. We're told that each transistor will sink about 0.1 milliamps of current from the positive power supply. And we're told the positive and negative power supplies, plus 15 and minus 15 volts. And we're also told to follow it up with an emitter follower output. As you can see right now, this is not an emitter follower output. This is actually a second stage gain block that I've put in. For this question, just ignore this part, that's the shaded part here where we're taking the feedback out from this transistor. Ignore this this transistor. Instead, we'll follow it on this question. We'll follow it with an emitter follower, where this will be an NPN transistor, and this ground won't go to the minus 15 volts. Instead, it will go to ground, and we'll basically take the output from this. So and also we won't have a feedback because we're not told to use feedback here. So this transistor will simply be grounded, and instead of taking the output from this side, we'll take the output from this side, because we want it to be in phase with the input, because if we take it from here there will be 180 out phase, but we'll take it from this. So let's go ahead and design resistor values. This resistor, these two emitter degeneration resistors used to set our gain of 50, and also let's set the resistor here that allows us to sink the 0.2 milliamps from the two transistors, each one be 0.1 milliamps. And yeah, so let's go ahead and design that. For this case, I'm going to use a voltage reference or a voltage regulator, the TL431, in order to set my base voltage, to set my current that flows through this, that sinks through this transistor. So if you quickly take a look at the data sheet of TL431, it's able to sink current of, let's take a look here. So this is the TL431. It's able to sink current. If you take a look here, I'm gonna highlight it. It's able to sink from 1 milliamp to 100 milliamps. So I will be able to sink about 10 milliamps of current through it to set the 2.5 volt reference that I need to set my my base voltage correctly for the bottom current source transistor. So let's go ahead and design it. Okay, so to recap, we're told that we're gonna have to sink about 0.1 milliamps of current through here and through here. And we're also told that we're supposed to follow the output through an emitter follower. As you can see, we have an emitter follower. Our load is not specified, so I'm going to specify our load to be, let's say, 10 kilo ohms. And basically, we'll have to design for that in order we can drive this properly. And also, we're told that our gain, so the total gain for this circuit, is supposed to be 50. And also we're told that basically those are the information that we need to design this amplifier for. And in order to design all of these resistors here, we're going to have to start by designing our output first. So our output, in order to get good signal swing, it has to be between VCC, the 15 volts, and ground. So this is going to be 7.5 volts. So we'll go ahead, start designing it from here. And as you can see, because we're following it through an emitter follower, we're not going to have the full signal swing that we could have utilized the way we're using our power supply, because you can see that our power supply is from 15 to -15, so we have 30 volts. So we could have used a full 30 volts of signal swing on the output, but because we're following it with an emitter follower, we're only able to do from VCC to ground. So if you remember, if you saw the circuit I worked on the other side, originally that I showed you at the beginning of this video, you can use that circuit to actually get the full signal swing. And in fact, most op-amps, that's basically what they use basically. So this is even, you can consider this tutorial like a discrete op-amp design. So if I have time, I'll make a video where we'll utilize this circuit with a proper 3-stage discrete op-amp that we can design to drive power amplifiers, for example. So that's in incoming videos when I get time. But for now, let's go ahead and design this. Yeah, just a quick note before we start designing, that I have terminated my input with 50 ohms because my generator up there has a 50 ohm output impedance. So just to match the reading on the scope here, as you can see, and the output of that generator, I have terminated my input to 50 ohms. So just to note that. And so let's get started. So if this is 7.5 volts, then if we go out by here, then we're gonna have to this point is gonna be 7.5 volts plus 0.7 volts, because the VBE drop here. So if that is the case, then we know this resistor here, we're gonna call it RC. So let's go ahead and solve it here. So RC, as you can see, is 15 minus 7.5 minus 0.7 divided by the current that we're given, which in this case is 0.1 milliamps. So RC is going to be, so let's put it here, 15 minus 7.5 volts minus 0.7 divided by the 0.1 milliamps. Then RC is 68K. So we have designed RC, and like I said earlier, we don't need to put a load resistor here, because we're not going to, this output is not going to get utilized, because we're told that this is a single input DC amplifier, a single-ended DC amplifier to a single-ended output differential amplifier. So because of that, we're not going to utilize this collector voltage. So I've removed the resistor here, so we don't have to worry about that. Next is we have to design this gain setting emitter degeneration resistors. So I'm going to call them RE. So basically what we have to do is we just take a look at this part of the differential amplifier, which is basically like your typical common emitter amplifier. Its gain is given by AV. Because this is a single-ended output, the gain is going to be divided by half. So it's going to be RC divided by 2 times RE, which is the emitter degeneration resistor, plus our dynamic resistance RE. So this is the gain. So the gain, because we're using a differential amplifier, the common emitter gain, which is normally RC divided by RE plus RE, it's going to get halved because of this arrangement, because we're using basically we're using these two, so we have to divide the gain by 2. So in that case, we're told the gain is 50. We know RC is 68K, and we're told this is going to be 2, so I'm going to take the 2, I'm going to call this 100. So if I call that 100, this will be RE plus, we know the dynamic emitter resistance, which is 26 millivolts divided by IC, which is 0.1, so this is 260 ohms. So this is 260. So if we solve for RE, we're going to get, so I'm going to put it here, RE equals, yeah, so it's it comes out to be to 420 ohms. So we have to find a standard resistor that's something close to that, and we'll use that. But let's consider the gain again, because now we're going to set, if we set our RE to 420, our gain is going to be close to 50, which what we want. But because we have this emitter follower getting directly hooked up at the collector, some of that, you know, some of the current is going to be shunted to here, so we're going to lose some gain, because we're going to lose some gain when the small signal is getting amplified because of this loading here. So basically what we have to consider is, if let's say this transistor has a beta of 100, so this load that we have chosen, which is 10 kilo ohms, is going to appear here as 1 mega ohms, because the input impedance looking into here is beta plus 1 times RL, which RL in this case is 10K. So 100 times 10K is 1 mega ohms. So if we were to draw our small signal for this case, the RL is going to appear in parallel with RC with a value of 1 mega ohms. So if I draw it somewhere here with my pencil here, so let me just erase this for ease of seeing what's happening. So what's happening is, basically when we do the small signal analysis, we're going to find out that our load resistance is going to appear as 1 mega ohms here. So if we take the parallel combination of RC and 1 mega ohms, which is, we designed it for 68K, 68K in parallel with 1 mega ohms is 63K. So if we recalculate now our gain, it will be 63K plus RE that we've chosen, which is 420, plus the dynamic resistance at that current of the emitter of this dynamic resistance emitter, resistance 260 ohms, we're gonna get approximately around 46. So really we're not fulfilling our gain requirement, because our load is it's too low because of this. So one way to solve this is we can use a Darlington. If you use another transistor here, if you use Darling transistor here, then its loading is going to be minimal, but then your frequency response goes down, because Darlingtons are not, they're slower devices. So I don't want to use that. In this case, what I'll do is I will actually lower RE. So if we take this 63K and recalculate again, we're gonna get, if we take this and recalculate for a new RE, so if we take this, call this RE, and we call this 100, and resolve this equation for RE, we're going to get our proper RE that will give us something for our gain greater than 50 with our emitter emitter follower output. It's going to be 370 ohms. So I've gone ahead and chosen a standard resistor of 330 ohms. 330 ohms will give us a really good gain. In fact, I have done the small signal analysis on the Maxima software. So if I show you some of the computations I performed, the overall gain, it's going to be... before I show you the actual calculation, I'll show you quickly the small signal resistance and the small signal equivalent circuit, I mean. For this circuit here is going to look like this, with the emitter resistance put in, the dynamic resistance put in, and the transistor the transistor model put in. So as you can see, this is the transistor 1 and this is the transistor 2. If we put that and we write two equations, actually three equations, one here, and one here, and we solve for the gain, that's VO over VS. So VS is, you can see that I have distributed it evenly on the two inputs because it's going to appear, half of it appearing here and the other minus half appearing here. So if we do this and we do the actual calculation, which I will show you here. So if we can just zoom in here. So as you can see, this is the first equation written on one side of the input of the differential amplifier. This is the equation written on the other side of the differential amplifier. And this is the output equation, and we solve for VO. And so as you can see, this is the actual transfer function between input and output. And if we put all our values here, as you can see, the 68 k ohms, the RC, our load resistor being 1 mega ohms, the gain setting resistor 330, which is the emitter degeneration resistor, our source impedance 50, and our alpha, which is beta plus, divided by beta plus 1, and we put RE260, we're gonna get 53.4. So basically this agrees with some of the measurements I did, which I'll show you in a bit. But what I'm getting at is basically is because of our, so if we get back here, because of our emitter follower output, our gain will be loaded, so we have to make sure that we set our gain setting resistor, which is the emitter degeneration resistor, to be appropriately. So we can recalculate it, and I've set it to 330 ohms. And now let's go ahead and design this current source really quickly so that we can sync the 0.1 and 0.1 milliamp current from both sides of the transistor, which add up to 0.2 milliamps here. So let's go ahead quickly design that, and we'll do a quick measurements and verify the calculated with the actual results. Okay, let's go ahead design this current source, or current sink to be exact. So what we have to do is we have to sink 0.2 milliamps from the differential amplifier. So as I said, I'm using the TL431 voltage reference here to set my base voltage. So if this is minus 15 volts, because this is hooked up in this manner where the reference pin is directly tied to the cathode, and the anode is directly hooked up to the minus 15 volts, and the cathode is tied to the base. In this case, the voltage reference is going to have 2.5 volts across it in this arrangement. So if this is 2.5 volts, then minus 15 plus 2.5 volts would be minus 12.5 here. So we're going to get minus 12.5 volts here, and if we drop by VBE, which is 0.7, this is going to be minus 13, basically minus 13.2 volts. So all we have to do now is calculate RCS, because we know the emitter current here will be close to the collector current. So so our RCS is going to be minus 13.2, because current is flowing like this, plus 15 volts, because this is minus, so minus 13.2 minus minus 15, which will be plus 15, divided by 0.1 milliamps. We're gonna get our RCS approximately to 9.1 kilo ohms, and that's what I have chosen for that case. And also we have to set our biasing resistor for this voltage reference. So I'm gonna sink about 10 milliamps of current. You can sink, you can do 1 milliamps, because like I showed you on the data sheet earlier, the TL431 also will be able to regulate the 2.5 volts at 1 milliamps. So but I'm using 10 milliamps here. So R1 is going to be 0, because current is flowing this way. 0 minus 12.5, which will be 12.5, divided by 10 milliamps. which will be around 1.2 kilo ohms. And I've chosen 1.2 kilo ohms. I think I've chosen 1 kilo ohms, sorry, 1 kilo ohms resistor. So, but you can also use 1.2. So we'll just slightly sink more current here, maybe 12 milliamps or so. Okay, now that we have designed our current source, I have put in all the values that we designed. I put in the 68 k ohm collector resistor, the two gain resetting resistors, the emitter degeneration resistors, put in my biasing resistor for the current source, and also the current setting resistor, and my load all built up here. And also the calculated voltages that we expect. As you can see, I didn't put in one voltage level, so let's add that up. Because this is going to be 0, then by the time we get down here, we're going to be minus 0.7 and a little bit. And since there's only a few drop, we expect this one around to be minus 0.7 or so volts, somewhere around there, right? So let's go ahead and verify this measurement on the built circuit. So the circuit is built here, so I'll quickly describe the circuit. There are the two differential transistors, and one thing about these transistors, ideally these transistors should be matched. If you can get transistors that are on the same die, so basically which have the same VBE, same temperature characteristics, same beta. If you can get those, then this differential amplifier will work really good, because of the matching required between these transistors. And for myself, I tested few transistors from the same batch to make sure that their characteristics are as close as possible. So for differential amplifier, note always that these two transistors should be matched, and they should be as close to each other as possible, so we have good temperature tracking as well. So anyway, so going back to the description of this circuit, so there are the two differential amplifier transistors. This is the current source. As you can see, these are the two 330 ohm resistors on the emitter, and this is the TL431 voltage reference. This is the 9.1 k ohms. As you can see, I think I'm using actually 10k here, if you see by the band, but that's okay. That's alright. It's close to 9.1k that we calculated. This is the 50 ohms on termination of the input of this transistor, and like I said, I'm inputting it on this transistor, and I'm taking the output from this side. So the phase of the input and output signals will be the same, because as this voltage goes higher, this transistor will try to go to the saturation. Basically, most of the current will go through this transistor, which means this current will go down, and if this current goes down, then this voltage goes up. So as you can see, as this voltage goes up, this voltage goes up as well, so there will be in phase. So note that if I put the resistor here and I took it from here, then the output will be inverted, so it will be 180 degree out. So anyway, that's something aside. So let's finish up on the description, and if we get a little closer here, there's the emitter follower output. There's my 10k ohm resistor to ground, as you can see with the bands, and some decoupling resistors here to keep the board quiet, and there's a 68k ohm for my load resistor. Okay, so let's do the measurements now. So what do we expect? First of all, we're gonna go measure here, and we expect 8.2. So let's take a look. Where is that? That's basically on this guy here, on the collector side, which is on this side of the resistor. So if I do that, what do I get? I get 7.938. So very close. We designed for 8.2. We get 7.9. Okay, so that's this point here. Let's go measure this point here. Where is that point? That point is here. which will basically, these two will have, let's see if the matching is good. So you can see minus 0.633, we expected minus 0.7, yeah, that's close. And let's take a look if the matching with the two transistors is good, and we get minus 0.6336 as well. So yeah, these transistors are quite matched nicely, and these are 1% resistors, so they're gonna be close enough. So yeah, and let's take a look here. What do we get here? We get here a minus 0.665. so if we subtract the minus 0.633 we got from this and we divide it by the 330 ohms, we're gonna get close to the 0.1 milliamps current that's flowing through these. And let's take a look here. How much would we expect here? We expect here minus 12.5 with respect to ground. So the TL, there's the TL31. So if we go and measure it on this side, I get minus 12.538. So very close to what we designed. And also we're going to go ahead and measure this part here, 0.6 drop from the minus 12.5. which is basically on this side here. The resistor goes from the base of this guy to ground. So if I measure here, so yeah, that's the base. Yeah, the base is minus 12.5, which I just measured, and I should be measuring on this side here, on this side here, right here. So that would be the emitter of the current source. As you can see, that's minus 13. Yep, so very close to what we designed. Okay, now let's measure the gain. So I'm inputting the, from my function generator, 0.1 volts peak to peak at frequency of 1 kilohertz. And if I turn on my if I attach my generator, so as you can see, this is where I'm inputting it. So the input is right here on this yellow wire. That yellow wire comes here where channel 1 is hooked up. So if I do that, as you can see, so if I do that, let's measure our gain. So our gain is, we're expected to be above 50. So take a look. I'm putting in 100 millivolts. In channel 2 the amplified is 5.16. So you can see 5.16 divided by 100 millivolts, we get 51.6. That's the gain. That's the calculated gain. That's not the calculated gain, I mean the measured gain. As you can see, we're satisfied our gain basically. And if you can see the output, I'm taking it here, this is channel 2, it's from the emitter follower output. So if we go, I was measuring at the base of the emitter follower, so basically I was measuring here at this point here. So if I measure it down to here, so if I go to here, I'm gonna get same thing, right? Because it's buffered output, right? So actually our gain slightly improved. As you can see, it's 52 now, because we're on the other side of the buffered output on the emitter follower output. So one more measurement that we can do is basically we could do the frequency response of this amplifier, but really we're not told to we weren't giving any information in regards to some bandwidth requirement that we had to fulfill. So yeah, so basically this is the design for question 5 of chapter 2 of the art of electronics on differential amplifiers. And I'd like to note one thing on this. As you can see, as I mentioned earlier, our signal swing is very low here. So as you can see, we can only swing between 0 and 15 volts, right? Our peak to peak will be slightly less than 15 volts peak to peak. So if I actually measure that until clipping, so what I'll do is I'll increase my input voltage until the amplifier clips. Yeah, before like I said, before I finish this video, let's take a look how we can predict the amplifier, where it's going to clip. So basically, at what input does this amplifier clip? So we can quickly do a quick calculation to figure that out. So if we go back to our drawing here, we know that when since we're taking our output from here and it's sitting at it's sitting at 8.2 volts, when the transistor fully saturates, this point is going to swing down to, we can find out, like all of the current that passes through here will shift to this. This transistor will completely cut off. So all the 0.2 milliamps of current will be flowing through this transistor. So this point, if we call it VC is going to be at that when this transistor fully saturates, 15 minus this resistor 68K multiplied by the 0.2 milliamps. This is our saturation, so VC sat if I call it. So this will come out to be 1.4 volts. And also we know that when this transistor is fully saturated, this transistor will be cut off. So all of the current will be flowing this way, so this transistor will be cut off. So this point will fully be 15 volts. So this point will be at 15 volts. So what do we have? We have a range that we can swing. This point, it can swing between 15 volts and 1.4 volts. So, and the midway point, which we're set it to by biasing correctly, it's 8.2. So from here to here, it will be 6.8. So if we multiply that by 2, we're going to get, so if we do that really quick here, 6.8 multiplied by 2. So our peak-to-peak output will be, before clipping, it will be 13.6. If we divide it by the gain to find the input voltage at which the amplifier clips, if we divide it by the gain, our gain, remember, we calculated was around, well, we measured it was 52. So 52, it gives us 261. So at 260 millivolts peak to peak, basically if I inject 260 millivolts peak to peak, that the amplifier will reach its full output swing. So let's go ahead and demonstrate that. So what I'll do is I'm gonna increase this to 260 like that. So if you take a look, and I'll measure where the amplifier is going to clip. So you can see that it clipped already. So I'll take a look here, the amplitude that I'm injecting. So let's verify. We said it was 260 is when it should clip. So there we go. So at 266 you can see that it's clipping. It's actually clipping a little earlier than that, and that's expected since that was a rough calculation. So if we go ahead and do the full, if we clip it completely, we'll take a look. So our output swing is actually from here to here, and you can see it's around 12.32. We calculated 13 point something, but yeah, close enough. So basically that concludes the question 5 on the art of electronics on the design of differential amplifiers. I hope this helps. Okay, see you later.